Let's take a look at this example. Here we will be using the normal to approximate a binomial distribution. So I hope you have seen this lesson. That way, when I do the problem, hopefully it will start to make sense. Let's see what we got here. Suppose the probability that a birth results in twins is estimated to be 0.016. Find the probability that at least 5, but no more than 15 births out of 1,000 result in twins. Use normal approximation to binomial distribution. So we know that for binomial, you'll find the probability of some event x, let's say x equals to little x, is going to be n, choose x, times little p to the x times q to the n minus x. So that's the formula for binomial distribution. Now we're not going to use that. Instead, we're going to be approximating it using the normal distribution, which means we need to use the z-score table. So let me show you which z-score table we're going to be using in this video. So we will be using this table right here. This one reads in a different direction of the normal curve. So as you can see, this table right here, as we have listed out the z-score vertically and horizontally, this will read area from 0 to this direction. So that will be the area under the normal curve. So just be mindful, if you're using a different z-score, you will get the same area, except you have to be careful which direction does it read the area under the normal curve. Is it to the left, to the right, or from 0 to the right? So we have to be very mindful of that. Okay, so let's go back to the question. So let x represent, that is our normal variable. So x is going to represent birth results in twins, because that is our event. And we're interested in what is the probability that at least 5, but no more than 15 births out of the 1,000. So 1,000 is going to represent your n value for the binomial. And the probability that the birth will result in twins, it's going to be 0.016, which is given to us right here. That is the probability of success of this event x. Then q is the complement of p, that's 1 minus p, so that'll be 1 minus 0.016. And that would give us, if you put this in your calculator, you'll have 0.984. Now the next thing we need to find is the mean. So for binomial, we know mean, we denote it by mu, that's going to be n times p. So here n is 1,000, p is 0.016. So that'll give you 16 for the mean. And we're going to need that for the normal approximation. Then we need standard deviation. For standard deviation, we have the formula, sigma is equal to the square root of n times p times q. So let's go ahead and substitute them and find q. That is equal to sigma. So that's going to be 1,000 times n, which is 0.016, and q, that is 0.984. Then if you put this in your calculator, you'll have sigma to be 3.97. All right, so let's hold on to these. Now let's try to answer the problem. We want the probability that at least 5, so more than 5, but no more than 15, so less than 15, so between 5 and 15. That's what we want. So we want probability that our birth will result 5 or less than or equal to 15. That's what that means. Now, since we're not going to use binomial, we're going to approximate by using normal. So I'll put the curly equal sign. So this is going to be probability of x is between new two x values. Now, here's what you need to do. Since the interval is from 5 to 15, we're going to extend this to the left 0.5. So instead of using 5, we're not going to use that. We're going to use 4.5. And then instead of using 15, we're going to be using 15.5. So you extend the interval to the left 0.5, to the right 0.5 to adjust that continuity correction for the normal approximation. So here I'm going to put 4.5 for the neo-x value, here 15.5. So that will be the values that we're going to find the z-score of, and then we can read off the area from the normal curve. So I hope that's making sense. Now let's find the z-scores for each of these. So this is going to be probability of, now here I'm going to put z instead of x. And for 4.5, so remember this formula that z is equal to x minus the mean over sigma. That's how you convert from a normal to a standard normal variable. So our x is 4.5. We're going to subtract the mean. Mean we computed to be 16. Standard deviation is right here. Let's use them. So this will be 16 over 3.97. And then here you'll have 15.5 minus 16 over 3.97. All right, and then you put those in your calculator. You'll have this is the probability of, this will give you negative 2.90, less than or equal to z, and then less than or equal to, if you put the second one in, you'll have negative 0.13. So those are the new z-score. Now let's draw the normal curve and see what is it that we're looking for, so we can figure out the geometry of the curve. So we know our normal curve looks like this, something like that. We know 0 is right in the middle. This is our z-axis. Now negative 2.90, let's say it's all the way here. Let's just say estimating, negative 2.90. And the negative 0.13 is perhaps right here. Negative 0.13. And we're interested in this area. That's the area we want because that will represent the probability that the birth results between 5 to 15 twins. Birth results in twins. The table gives us area from here to this way. And we know there's 50% under the curve in this direction. And by using symmetry, there's 50% on the left of 0. So what we're going to do, we're going to imagine reflecting this region about the origin and then figure out the geometry. So here's how it's going to look. So if you reflect it over, a negative 0.13 will be reflected right here. We're reflecting it about the mean. So this will be positive 0.13. And negative 2.90 will be somewhere up here. It'll be positive 2.90. So instead of finding the area of that green on the left side, is the same thing as finding this area right here on the right side, because by symmetry, both regions contains the same area, so same probability. So what we're going to do, we're going to use our z-score table, but again, our z-score will provide area from here to this direction. So that means we need to do a little subtracting. If you read up the area for z of 2.90 for this value, you're not going to get just all of this. You're also going to get this part. So you're going to get all of that area for z of 2.9. So we can hold on to that and then find the area of z of 0.13, which will only provide this. That means we can subtract the smaller area from the bigger area. That will give us just this portion right here. So hopefully that makes sense to you. So we're going to do it this way. So we'll find the probability of z of 2.90. And then we're going to subtract the probability of z of 0.113, because that will give us only this small region right here. Okay, so let's read it off. So let's go to our z-score, 2.9. So on the vertical direction, we're going to look for 2.9. So let's scroll down. 2.9 is right here. And then 0.00. So that means the area should be 0.4981. So we found our probability for z of 2.90 to be 0.4981 minus, now for 0.13, we go back to the z-score table. So we'll look for 0.1 in this direction and then 3 this way. So that's 0.13. So the area seems to be this point right here, 0.0517. So let's put that down. So this will be 0.0517. And then you subtract them. So this will give you 0.4464. Again, approximately 0.4464. Again, we're approximating. Remember that. That's so we extended the interval 0.5 in both directions. Now, just to give you a little bit of more illustration on what is the we did. So this z-score gave us this area. So here's our normal curve. And so this was 0 right at the center. So let's just say, right, that was the normal curve. So this is 0, this is z. So here is, let's say, 2.90. So when we read the table, it gave us all of this area. But we don't want all of that. We want it only between this and this. So then we found the area of this z-score, which was for 0.13. So if you draw another normal curve, sorry, my pictures are not symmetrical. Hopefully you can draw better curves. So 0.13, let's say it's right here. So this gave us the area of this region. So if you just highlight that using our z-score table, that's the area it gave us. So that means if you wanted only for this to that, so you see that we take the bigger area and we subtract away the small area. And that gave us just the leftover, which is this region right here. And by symmetries, this is the same as this area right here. That's why it's the same idea. I hope that makes sense. Take care, everyone.